Ever wondered what a sizzling pan of food and a rusty old bike have in common? Well, they're both going through massive transformations, right down at the molecular level. Today, we're going to crack the code on these chemical reactions and see how they literally shape the world around us.
I mean, just think about it for a second. Milk turning sour in the fridge, an iron pan getting that reddish-brown rust, the food you eat being digested, even the air you're breathing right now. These things are happening all around us, and inside us every single day. They seem totally different, right? But nope, they all share one big secret. They are all chemical reactions.
That's right, they're all chemical reactions, a process where some substances, well, they transform into totally new substances. And here's the cool part. We don't have to just guess when a reaction is happening. There are some really clear, telltale signs we can actually see. So, to find our first clues, let's check out a classic experiment. Picture this. You take a shiny little strip of magnesium ribbon. You hold it over a flame, and bam! It just erupts in this incredible, dazzling white light. And after the show is over, all that's left behind is this white, powdery ash. So what just happened there? We saw a change in state, right? The solid metal ribbon turned into a powder. And we definitely saw a change in color. It went from that shiny metal to plain white. These are the classic signs that a chemical reaction has just gone down. Others include a gas bubbling up, or even just a change in temperature.
Now, trying to describe all of that in a sentence, it gets pretty wordy fast. So, scientists came up with a kind of special shorthand, a universal language to describe exactly what's going on, and they call them chemical equations.
And just look at the difference. On one hand, you have that long, clunky sentence. On the other, you have a simple, elegant equation. Mg plus O2 gives you MgO. It's clean, it's quick, and any chemist anywhere in the world knows exactly what you mean. But there's one golden rule to this new language, and it is a big one. The law of conservation of mass. Basically, it just says that you can't create or destroy atoms during a reaction. Whatever stuff you start with, your reactants, you have to have the same amount of stuff in your final products. Nothing can just pop into existence or vanish into thin air.
So let's go back to our magnesium equation. On the left side, you see we have two oxygen atoms, right? In that little O2 molecule. But then you look on the right side, in the MgO, and there's only one. So, wait a minute, did an oxygen atom just disappear? No way. It just means our equation isn't quite finished yet. It's unbalanced.
So, to make sure our equations follow the law, we have to balance them. And you can really think of it like solving a little puzzle. We're going to walk through another common reaction to see exactly how it's done, when iron reacts with water.
Okay, step one is just taking inventory. We count up all the atoms on each side of the arrow, and you can see right away the scales are totally tipped. The numbers for iron and oxygen just don't match up between the left side and the right side. That's the puzzle we need to solve. A good trick is to start with the most complicated looking thing, which here is the iron oxide on the right. To get the 4 oxygen atoms on the right to match, we need to put a big 4 in front of the H2O on the left. Now our oxygens are balanced. But uh-oh, you see what happened? We just created a new problem. Now we've got 8 hydrogens on the left.
No worries, we can fix that pretty easily. If we have 8 hydrogens on the left, we just need 8 on the right. So we'll put a 4 in front of the H2 molecule on the product side, and boom, now our hydrogens are balanced too.
And the last piece of the puzzle is the iron. We've got 3 on the right, so we just need to pop a 3 in front of the iron on the left. And there you have it. Take a look. Everything matches. The puzzle is solved, the equation is perfectly balanced, and the law of conservation of mass is happy.
All right, so now that we've got the language down, let's start looking at the different kinds of stories these equations tell us. Because even though there are countless reactions out there, most of them fall into a few major categories. It's kind of like genres in a library.
First up, we have the combination reaction, and it is exactly as simple as it sounds. 2 or more things combine to make one single, more complex thing. It's like mixing flour and water to get dough. A perfect real-world example is when you add water to quicklime. It combines to form slaked lime and gives off a ton of heat.
Next is the total opposite, a decomposition reaction. This is where one big compound breaks apart into smaller, simpler pieces. It's like a Lego castle falling apart into a pile of individual bricks. For instance, if you heat up those green ferrous sulfate crystals, they break down into a reddish-brown powder and a couple of sulfur gases. Then you've got the displacement reaction. The best way to think about this is like a sports team. A more reactive, or you could say stronger element, comes along and literally kicks a less reactive element out of its compound, taking its place. You see this when you dip an iron nail into a blue copper sulfate solution. The iron is more reactive, so it boots the copper out, and the blue color of the solution starts to fade.
And finally, for our main types, we have the double displacement reaction. Just picture two couples on a dance floor who decide to swap partners. That's exactly what's happening here. The ions from two different compounds just exchange places, and they form two totally new compounds in this elegant little switcheroo.
Now, beyond these four main types, there's another really powerful way to look at chemical reactions, and this one has everything to do with the movement of oxygen and hydrogen. It's the idea of oxidation and reduction.
You should really think of these as two sides of the very same coin. Oxidation is when something gains oxygen or loses hydrogen. And reduction? It's the exact opposite, losing oxygen or gaining hydrogen. The thing is, they almost always happen together in what chemists call redox reactions. It's this constant give and take that powers everything from batteries to our own bodies.
Okay, so we've learned the language, we've learned the main types of reactions. Now let's bring it all home and see how this new knowledge helps us finally understand those everyday mysteries we started with.
Remember that rusty iron pan? Well, that process has a name: corrosion. It's the slow, gradual destruction of a metal because of its environment. And what's at the very heart of rusting? You guessed it, a reaction we just learned about: oxidation. The iron is just slowly reacting with oxygen from the air and water.
And what about food going bad? That's oxidation too. When the fats and oils in our food react with oxygen, they become rancid, and that's what makes them taste and smell awful. And here's a fantastic real-life example. Ever wonder why your bag of chips is all puffed up with air? Well, it's not air. It's filled with nitrogen gas, which pushes all the oxygen out and stops the chips from oxidizing and going stale.
So, from a dazzling flame at a lab to the satisfying crunch of your favorite snack, our world is just this giant stage for constant chemical reactions. So the next time you rip open a bag of chips, you'll actually know about the invisible chemical war that was won just to keep them fresh. Thanks to a little nitrogen, they were saved from the relentless power of oxidation. Chemistry, it turns out, is literally everywhere.